Hi, I'm Boya. I'm very excited to present to you today our paper, Generative Modeling of Weights, Generalization or Memorization. This is joint work with Yida, Zhiqiu, and Zhuang. Generative models can produce high-quality and novel images and videos. Building on this success, they have been extended to various different modalities like radar, robot behaviors, protein, gene sequences, and many more. Recently, generative models have also been extended to generate neural network weights. These methods collect a set of high-performing checkpoints for a particular task and architecture and learn a generative model over them without direct access to the training data of the downstream task. While the prior studies primarily evaluated the methods based on the downstream performance of the generated checkpoints, a critical question remains. Have the generated models learned to produce meaningfully distinct weights that generalize beyond the training weights, or do they merely memorize the training data? In this study, we analyzed four representative generative modeling methods for weights: hyperrepresentations, G.pt, hyperdiffusion, and pdiff. To evaluate the novelty of a generated checkpoint, we compare it to its nearest training checkpoint under L2 distance. In each of the 12 heat map, the first row shows a random generated checkpoint, and the three rows below are the three nearest training checkpoint. Each column is a randomly selected parameter index. We observe that, for almost all generated checkpoints, there's at least one training checkpoint with nearly identical weight values. Quantitatively, we find that for all methods except pdiff, the generated checkpoints are significantly closer to the training checkpoints than training checkpoints are to one another. pdiff is a special case because, unlike other methods whose training checkpoints are saved from different runs, its training checkpoints are saved from the same training run at consecutive steps. This discrepancy in distance distributions tells us that the generated checkpoints are less novel than a new checkpoint trained from scratch. On top of weight values, we also compare the behaviors of generated models and their nearest training models. We plot the decision boundaries for classification models and show renders of the 3D shapes represented by neural field models. We can see that the decision boundaries and 3D shapes are almost identical. This shows us that the generated models also behave highly similarly as the training models. For classification models, we quantify the novelty in model behaviors using similarity in predictions to training models, and we'd prefer generated models with high accuracy and low similarity. For neural field models representing 3D shapes, the performance and novelty are measured using distances to test and training set shapes, respectively. We compare the generated weights with a simple baseline that adds Gaussian noise to training weights. We can see that for all methods except pdiff, in terms of this trade-off between model performance and novelty, the generated models in fact doesn't outperform the noise addition baseline. So, why is pdiff different? We can see that pdiff's generated weight values concentrate around the average of the training values. It is known that averaging the models fine-tuned from the same base model can lead to improved performance, so we hypothesize that the generated models may achieve higher accuracy by interpolating training weights. To check this, we introduce two baselines that approximate interpolations of training weights, named averaged and Gaussian on the figures. The left plot shows the same accuracy novelty trade-off, and the right plot shows the weight distribution using Disney. We can see that the generated models resemble the interpolation baselines in both behaviors and weight values. In image generation, adjusting training length, model size, and regularization can reduce memorization. We test if this also suffices for weight generation. We use the average L2 distance between generated checkpoint and their nearest training checkpoint as a proxy for novelty, and measure accuracy for classification models, and MMD for neural field models representing 3D shapes to evaluate performance. We can see that the adjustments do not alleviate the memorization issue. None of them can substantially improve novelty without degrading performance. Some transformations of neural network weights can leave the function of the network unchanged. These result from symmetries in neural networks. For instance, permutation symmetry means that one can permute the hidden neurons of a network without changing its function. Hyperrepresentations and G.pt use this permutation transformation to augment weight data. Does this kind of data augmentation let generated model truly capture weight symmetries? We test this by feeding hyperrepresentations an original model and its transformed version. If its transformation invariant, the pair of reconstructions should express the same function. To check this, we measure the accuracy and behavior difference between each pair of reconstructions. Permuted and scaled correspond to two types of transformations. The large differences show that hyperrepresentations is not invariant transformation despite being trained with permutation as data augmentation. We also add 1, 3, and 7 random weight permutations to train hyperdiffusion, which doesn't use augmentation by default. Yet, even when we only add a single permutation, hyperdiffusion fails to produce meaningful shapes. Thus, we find that data augmentation alone is insufficient for generated models to learn neural network symmetries. To sum up, we find that generated models of weights show clear patterns of memorization. This is demonstrated in both weight values and model behaviors of the generative checkpoints, and in particular, we find that the generative models fail to outperform some simple baselines for creating new model weights. More broadly, these results highlight the need for more careful evaluation of generative models in new domains. If you're interested, you're absolutely welcome to check out our paper for more details. Thank you so much for listening.